I want to know about that picture. How on earth? What is going on with that picture? What is going on there?
In fact, I like to start with this image. This is a good conversation starter because I live in New York City, and as you know, New York is one of the worst places for astronomy. Yeah. So, and one of the things I noticed as you guys were pulling up pictures is I'm a professional astronomer, but my pictures are never as beautiful as yours. But anyway, this is an artist's impression.
I saw the theory code.
Either that or so, it's big in 1974.
Yeah, exactly. Well, yeah. So this is an artist's impression of what New York City would look like if you shut off all the lights. And you know, I think New Yorkers, whenever I give talks in New York, it's one of these things where a lot of New Yorkers are incredibly disconnected from the sky. They almost don't even know that there's a galaxy up there. Because the concept is you can only see maybe one or two stars, and most of the time it's actually planets. And here it sounds like you guys have a much better opportunity to see the skies when it's not covered. And so, of course, if you were to look up, you know, the stars don't, they're not just in some, you know, uniform distribution around the sky. They fall in a nice band, which is called the Milky Way. And so this is the artist's impression of our galaxy, the Milky Way, which is just a collection of dust, gas, stars, and dark matter, all held together by their mutual gravity. So one of the downsides to living in the northern hemisphere is that if you get on a plane and fly down to the southern hemisphere like Chile, the most majestic galaxy is down there. So the center of the galaxy actually is just barely observable from the northern hemisphere. And so if you were to get on a plane and go down to Chile, this is what the galaxy might look like. And so you can see all of the center of the Milky Way and its kind of beautiful majesty. Of course, you have a galaxy here that is not some blob. It is actually has some structure to it. You know, a disky component here, a bulge component here, and you have the beautiful dust lanes. And so, you know, when I got into astronomy in middle school because of a girl. And then that kind of progressed as well, she moved away and we didn't really talk very much, but the love for astronomy still remained. And but then when I went off to graduate school, I saw this image, and I became really interested in asking questions about how galaxies, like our galaxy, how do they form, how do they assemble, how do they evolve, and what are their structure? I mean, you can see that there's not, you know, it's not just some amorphous blob here. There's really structure within this galaxy. And so these questions form the fundamental questions of galactic archaeology. So these are the fundamental questions that I ask every day, and that observational astronomers around the world that are studying our galaxy and other galaxies are asking on trying to figure out how galaxies in general form. You'd be surprised. One of the things that I learned going through graduate school was how little we know. When I was an undergrad, my professors all told me that this was a solved problem because everybody in the US is working on cosmology because that was the hot topic. And then people switched to now working on exoplanets, trying to find other planets. But the Europeans are still working on stars and still working on our galaxy. And it was when I went to Europe to do my PhD that I realized that our galaxy is not a solved problem. There's lots of interesting problems surrounding our galaxy. Right, so that is what galactic archaeology is about. Bless you. Before I get too far into galactic archaeology and talking about stellar fossils, I kind of want to remind everybody what a star is. Does everyone know what a star is?
It's a ball of gas.
What is a star? It's a massive gas, but there's something special about it.
Fusion.
Fusion, yes. So, so obviously a star is just a hot ball of glowing gas, but what distinguishes a star from any old, I mean, for example, neon lights that you see outside of a bar, they're hot balls of glowing gas as well. But what distinguishes those from, say, a star is that a star is undergoing nuclear fusion at its core. And it's producing its own energy at the core via nuclear fusion. And so stars are formed essentially by taking massive, giant molecular clouds that can be hundreds or even tens of thousands times the mass of our own sun, and collapsing that gas down. And as it collapses, it gets hotter and hotter and hotter. And so it collapses over time, it gets hotter and hotter and hotter. And as it gets hot, it starts to occur, nuclear fusion starts to occur in its core. So this is just a schematic of what nuclear fusion is. So the video will start in a second here, but I just want to kind of describe, this is all taking place inside the core of the star after that gas cloud has contracted and become really, really hot. These are two protons, which are hydrogen atoms. And protons are like charges, right? So they're both positive charges. And the thing we all learn about positive or like charges is that like things, like charges repel, and opposite charges attract. I hope that's not true of human beings. Because if I ever have a spouse one day, I hope they're not too much like me. They're too different. So as we start this movie, this goes, yes. Ah. Turns out this is actually kind of hard. So the two protons, the velocities of two protons are high enough that they fuse together and create heavy hydrogen and then two other particles. And when you get another proton that fuses onto that heavy hydrogen, creating helium and a little bit of gamma ray radiation. So that's where the energy is coming from that fusion reaction. And then you have these two hitting each other, creating helium. And so that's where the energy is all coming from. And if this goes out, there's one other point that I want to make about this, which is an interesting fact about the sun, is that this next reaction will create the energy and that gamma ray radiation. There it goes, right there. But do you know how long it takes for energy to actually leave the core to hit the surface?
38,000 years or so, I think.
Million.
Debatable.
It's debatable, but it's on the order of about 100,000 or a few 100,000 years. And the reason why it does that is because it takes what we like to call in astronomy the drunken walk. So for the people that are old enough in the room who have had glorious nights out and have come home or tried to wander home and drunk, you'll kind of get what I mean. So essentially what's happening is that the photon, as it leaves the star, bumps into another atom, the atom absorbs it, it goes off again, bumps into another atom, the atom absorbs it, you get another emission, it bumps again, you get another emission, and it keeps going in this random walk out of the star. And the larger the star, the longer it takes. And so for a star like the sun, it takes on the order of a few 100,000 years for a gamma ray created in the core to actually make its way out to the surface and to our eyes. And so that's what stars are. That's how they shine. That's what happens. And a galaxy, like our own, the image that you've seen before, is just simply a collection of stars, dust, and gas, and dark matter, and all kinds of things. And so in this system, does anybody know about how many stars there are in our galaxy?
100 billion?
100 billion?
On the order
Billions and billions.
on the order of about 100 billion. So we're just one of 100 billion stars in this system. And
Why have we heard numbers like 200 billion? I mean, people throw around 200 billion.
right. So there's one thing that we'll always say in astronomy is that if you're in a factor of 5, it's good enough for government work.
Factor of 5.
Yeah. So order of magnitude estimates are oftentimes what astronomy runs on, because the reality is, what's the difference between 200 billion and 100 billion?
Yeah.
Not much. And so the way this is often done is people obviously don't count the stars. They use a mass function, and then they try to develop an understanding of how the stars are distributed in the galaxy, and then they build a model. So the exact number is not well known. Yeah.
Do you have any idea, roughly speaking, how many known galaxies in the known universe?
That's a very good question. I was just going to point out very quickly before I answer that there are 2 other small galaxies down here, the large and small magellanic clouds, which are galaxies outside of the Milky Way that the Milky Way is eating up. In terms of the number of galaxies in the universe, that's again a hotly debated question. We know that it's probably more than a few trillion, but again, it's a very hand-waving way, because it's hard to count, and on top of that, one of the real serious problems is that all of the galaxy surveys always point out of the plane of the galaxy. They never point in this direction because there's so much dust that they can't see behind it. So the estimates are still somewhat biased, because where you can look in space is a little hard.
But it's generally thought it's a couple of trillion, you said?
I would say at least, yeah. But if again, probably order of magnitude. take with a grain of salt. So yeah, so this is what I study. I study the Milky Way, and the way I like to describe galactic archaeology at a kind of a cocktail party is kind of like Indiana Jones, right? So you have Indiana Jones, and he goes off and finds fossils in somewhere in the world, and then he tries to piece together how ancient civilizations have come about and how they form and how they've maybe evolved over time. And as a galactic archaeologist, we do something similar. We take stellar fossils and we try to figure out how the galaxy, or how galaxies in general, form. And this makes our Indiana Jones jealous, of course. But every star in the night sky is a fossil for two reasons. So the first is that, of course, distances in space are vast. So, and there's a cosmic speed limit, which is the speed of light. So a star on the other side of the galaxy, which is about 100,000 light years away, you're not seeing that star as it is now, you're seeing it as it was 100,000 years ago. It's the same thing with the sun. The sun's about 8 light minutes from here. So if you were to look up at the sun, which you shouldn't do without proper protective lenses, of course, but you guys all know that because this is an astronomical society, you're not seeing the sun as it is now, you're seeing the sun as it was 8 minutes ago. So that's one reason why stars are fossils. But the second reason, and the more, in my opinion, the much more powerful reason why stars are fossils is because if you look at their chemical fingerprint, that is, if you look at the chemical abundances on the surface of that star, it hasn't changed, more or less it hasn't changed over the course of its life. So if you look at the sun is about a 4.5 billion year old star. And if you look at the chemical composition of the star, of the sun, you're seeing that chemical composition of what the universe was doing about 4.5 billion years ago. So if you look at a star that's 10 billion years old, you can really start to look at what the state of the gas was doing in the universe 10 billion years ago. It's the same concept with ice cores. People go to Antarctica, they drill ice cores, and they try to piece together what the atmosphere of the Earth looked like, 100 million years ago, because you can take the ice cores, you can cut them, and then you can look at what the gas was doing. It's the same concept that we do with stars. So this is what I've been working on, and this is what I do as a galactic archaeologist. I look at a large collection of stars on the order of hundreds of thousands to billions at a time, and I look at their properties and I try to understand how the galaxy formed. So how did the galaxy form? If you were talking to a Greek mythologist, they would say this started with Hercules. So the story goes that, so this is a very famous painting by Rubens.
Exact copy.
Exact copy. Brought it here just for you. And so the Greek mythology story of the Milky Way is that Hercules, which is pictured here, was born to Zeus and a mortal woman. And so Zeus was very fond of Hercules, and so he came to take Hercules to his wife Hera to breastfeed, because it was believed that Hera's breast milk would give him immortal powers, and it was nourishing and so forth. But the problem was Zeus did this when Hera was sleeping. So Hera woke up and realized there's this random child, that I'm breastfeeding, and she pushed the child away and out squirted some milk, and that milk became the Milky Way. So that is the Greek mythology story of how the Milky Way came to be. So obviously we don't think that's actually how the Milky Way came to be.
Could have.
Could have happened, but probably not. And so how did the Milky Way actually come to be? Well, and so the way that we do this as astronomers and astrophysicists is we basically, of course, go through the scientific method. So we start with the question. That's the question. How do galaxies like the Milky Way form? And the next step of the scientific method is you need to create a hypothesis, right, so that you can test that hypothesis. And so what we do is we take all the knowledge of physics that we have, we dump it into a computer, and so this is a computer simulation of how galaxies form. And so what we think happens based on our simulations is that you take small subgalactic units, and by a mutual gravity, they all coalesce in a process called galactic cannibalization. And this big galaxy in the middle is going to eat all of the small galaxies around it and grow. And as it grows, it produces more stars and produces structures. You can see that the galaxy itself is not unstructured. There's structure here. There's rings, there's shells, there's tidal tails here going around. And so we basically build simulations like this for how galaxies form. And then once we've made this model, we can then observe the model. So now that we have that model, we can say, how are the stars positioned? What is the distribution of stars in that model? What does our model predict for the motion of those stars, the velocities, if you will, of those stars? And what does the model predict for the chemistry of those stars? And so astrophysicists will create these models and give me all of that information of what they're predicting for the positions of the stars, the motions of the stars, and the chemistry. And then I am an observational astronomer, so then I will go out to my telescope. In this case, I'll be talking about Gaia, which is pictured here. I go out to my telescope and I actually measure, physically measure, well, I can't physically measure, I guess, but observationally measure, the positions, motions, and chemistry of those stars. I compare them to the simulations that that my colleagues have done, and then we can go round and round and develop a better understanding of how the galaxy forms. So this is the process of how we do galactic archaeology. So the telescope that I use a lot of ground-based telescopes. I am one of the very few observational, I think it will be my generation, will probably be the last set of observational astronomers that physically go to telescopes. It's now all being done in survey mode, and a lot of observing astronomers are now doing it remotely. So I have actually physically gone to many telescopes around the world, but in fact on Friday I'll be observing at a telescope remotely. So that's becoming a bigger component of what we do as astronomers. So this telescope is called Gaia. It's in space. How many of you guys have heard of Gaia? It's been in the news recently. Oh, everyone, great. So Gaia is a purely European mission. Purely European. And the reason why it's purely European is because the Americans, for whatever reason, believed that all stars in galactic astronomy was a solved problem. So like somehow the astronomical community in America got together in like the 1950s and 60s, said stars is a solved problem, we're going to move on to cosmology. Europe realized stars are not a solved problem and kept going. And now this is a purely European mission because America didn't want anything to do with it. But the Europeans, in their very kind wisdom, were very nice to allow all of the data to go public immediately. So once the data has been processed, all of the data went public, even for American astronomers. And so the reason why I went to go train in Europe is because they care about galactic astronomy, and now America's waking up to this and now caring as well. So Gaia is called the Billion Star Surveyor. Its mission is to produce the most precise 3D map of the galaxy ever attempted by human beings. So it's only going to measure the position and motions for about 1 billion stars in the sky.
Is that done by parallax?
Yeah, which I'll describe next in case anybody doesn't know what parallax is. But yeah, so Gaia will actually produce parallaxes for about 1 billion stars. And it will obtain 3D motions for about some very large subset of that number of stars as well. It costs about €1 billion, so it's said to be about €1 per star, roughly, which is what, $1.20, $1.30? Ish. Somewhere around there, $1.20, $1.30. The great thing about Gaia is that we thought we were going to get 1 billion stars. The second data release, which was like Christmas morning for me, was April 25th. Like we all, were in New York City, huddled around computers, getting the data as quickly as we could. And what we found out is that there's actually 1.6 billion stars in that catalog, not just 1 billion. So we got even more data. We got almost twice as much as we expected. So to give you an idea of why Gaia is going to revolutionize astronomy, back in the 90s, so I was born in 91, and back in the 90s, Hipparcos was launched. And so for basically my entire life, galactic astronomy and what we knew in terms of position and motion information was all confined to this little itty bitty circle. It was the closest about 100,000 stars. That was Hipparcos. And Gaia is going to expand that from this little bubble to this. And that's just positions. That's just detailed positions and velocities. If you're not so interested in the position, you can extend to this. So where Hipparcos was only giving us sample sizes of 100,000, and that was considered big data, we now have 1.6 billion. That's now big data. So we're in a completely new era as of April 25th in galactic astronomy and galactic astrophysics. And it's a really exciting time. Yeah.
One of the things to note, we saw the pictures of the occultations.
Mhm.
Because of Gaia, some occultations actually happened because it moved the star position 20 miles.
Yeah.
So people now knew that they were in position to take pictures where they wouldn't have been in position, because it might have been over the water.
Oh yeah.
Because of the improved accuracy of the star, of the background star you were using for the occultation.
Right.
That's interesting.
Gaia will also actually do near-Earth asteroids, or it's doing some near-Earth asteroids because it's looking through the asteroid belt, as on top of pinning down the reference frame at micro-arcsecond levels. Right, so I kind of want to move on to what Gaia is giving us and what I do. And so these are the tools of a galactic archaeologist. The tools are positions, velocities, which are how the stars are moving, and the chemistry. And so I'll go through each three of them kind of very briefly, just to give you an idea of how we do each one of them, how we measure each one of them. And so my hope is that by the end of this presentation, you'll have a little bit of an idea of not only what galactic archaeology is and how it's done, but what these tools are and how we use those tools. So somebody said parallax earlier. Positions are all measured with Gaia through parallaxes. So for nearby stuff, you can do parallaxes. And the idea is I think, fairly simple. It goes back to high school geometry. You have a very distant set of background objects, and you have some stars locally. And these distant set of objects, in Gaia's case, are actually quasars on the other side of the universe. So they're really, really far away. And then more locally, you have your stars in the galaxy. And if you observe a star in June, relative to the background set of objects, it will look like it's in position B. 6 months later, if you go back and take an image of that star in December, it will look like it's in position A relative to the background. So the easiest way to describe, does everyone know what parallax is? Okay. So the easiest way that I have of kind of really kind of pushing this forward is if everyone can hold out their arm like this, with their thumb up. And if you look at that and you close one eye and you blink back and forth, your thumb appears to move relative to the background. Now put your hand really close to your face and do the same thing. And it should be moving much more drastically when it's close and much less drastically when it's far away. So in fact, the distance is it's inversely proportional to the parallax angle. So that angle is called the parallax angle, and it's inversely proportional to the distance. So the further away you are, the smaller that parallax angle is going to be. We use it all the time in our own daily lives for depth perception. That's why our eyes are separated the way they are, so we can actually perceive depth. And so that's how we measure positions in the universe, or at least in the local universe. And from these positions, you can get an idea of how the galaxy is structured. And so this is just an example, just a very basic schematic from an Astro 101 course on using those positions to then understand something about the structure of the galaxy. And so from using these kind of parallactic positions, we know that the galaxy has a disk component. We know the galaxy has a bulge in the center. And we know that it has a halo of stars around it. And currently there's a slight controversy, but I think it's almost been resolved. That disk has a thin component and a thick component. And you can think about that as like a crepe versus an American pancake. Like, you know, so there's a thin disk, which is what the sun lives inside the thin disk, which is the crepe. And the thick disk is created of more older stars that have undergone more collisions with stuff, like more gravitational interactions with stuff nearby. So their kinematics, their motions are hotter, so they're thicker, if you will. And that creates the fat American pancake. And then the halo has the hottest kinematics, or hottest motions and so forth. And the bulge is very interesting. For a long time, the bulge was inaccessible to us because of all the dust. If you just look towards the center of the galaxy, there's so much dust. And the way to get around that is you go to the infrared, because the infrared can peer through the dust. And so just recently, we now have new technology where we can actually peer through that dust with infrared spectroscopy and really start to understand the chemistry of the bulge. And we now know the chemistry of the bulge is very different than the chemistry locally. And so that's something that we're really interested in working on.
Whoa, how different? In what way?
Very different. So for example,
more hydrogen and less
more
heavy metals?
iron, much more iron.
More iron?
More iron and more magnesium, for example.
Are you going to explain like what we talked about at dinner with you're observing? I hope you talk about that because it goes right into what he's saying.
So I won't talk about it,
Okay.
but I can.
Okay.
But I can,
All right.
which is that essentially what we think is happening is that this bulge component formed very rapidly, incredibly rapidly. And there were many, many generations of stars going off really quickly, and that blew up the amount of iron. You need stars to create iron, of course. And as those stars explode, they explode their enriched guts into the interstellar medium to create a new generation. There were so many generations of stars here that produced a large amount of iron. There weren't as many generations of stars here because the star formation rate, is what we call it, was not nearly as high. It's basically like, this is New York City, and this is Westport. Right? New York City, there's tons of stuff, tons of action, all lights, all the time, go, 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 right? Lots of action going on here. Westport, not so much action, right? So there's a lot more, maybe, I guess, for lack of a better analogy, maybe there's a lot more babies being born here than in Westport, for example. The same is true about stars. There's a lot more stars being born more quickly here in the center of the galaxy, creating lots more iron and magnesium. So the chemistry looks different here than it does here. And so a project that I'm working on now is there are some stars that we think have been ejected by the supermassive black hole in the center of the galaxy. We found with Gaia DR2, with the Gaia instrument. And one of the project that I have on the telescope in a couple of nights will be, we're actually going to be looking at these very fast moving stars and try to see if their chemistry is consistent with being very, very, very metal rich, which means they come from the center of the galaxy or not.
And just to kind of go on to that, these stars are moving at 1,000 kilometers an hour.
Kilometers per second.
Sorry, 1,000 per second.
1,000 kilometers per second.
So the other idea is that if they're not metal rich, they came from
somewhere else, and very likely have come from another galaxy. Yeah. So you can actually use the chemistry of a star to tag, and I'll get to that part later. All right, so the last thing, or the second tool we use is velocities. And so this is just showing how something called proper motion, how we measure velocities in space. One way is through what we call proper motion. And so if you take an image, this is a star, a set of background stars which are very distant, and a foreground star that's moving. And if you take that observation in 1985, 1990, 1995, and 2000, and 2005, the star appears to move. And that's because it's actually moving across the sky. It's literally moving across the sky. And you can combine this with the distance of the star to actually to figure out how fast it's moving along the tangent motion, if you will, along the tangent along the sky. And so, in fact, this is what Gaia is doing. In addition to getting parallaxes, it actually will take measurements over the course of a 5-year period and be able to see how fast stars are moving across the sky in this way, through proper motion. And that gives you the velocity of the star. And so an example of this is one of the things that's been done with this second data release that came out in April is Gaia can actually see the LMC. It can see individual stars in the Large Magellanic Cloud. So here's an image. This is a Gaia image of the Large Magellanic Cloud. So this is what Gaia actually sees. And this is the proper motion vector for an individual set of stars in the Large Magellanic Cloud that Gaia saw. That's cool. And you can beautifully see that the Large Magellanic Cloud is rotating that way, because you can actually measure how the individual stars are moving across the sky. So that was actually, I found really, really cool. And so that's one way that Gaia is measuring positions and motions of stars.
What's the rotation of that? How fast does the Large Magellanic Cloud rotate?
I don't know in kilometers per second, but it's a little bit, I know that it's slower than the Milky Way. It is
The Milky Way takes, what, about a couple million years to do?
250.
250?
Yeah, about 220 million years to rotate at the solar circle, at the sun's circle. And it likely has a lot to do with the amount of dark matter, in terms of both the size in terms of mass of the galaxy, as well as the dark matter material content that's there. Yeah, did you have a question?
Yeah, I was just going to ask you, does the velocity of the galaxy have anything to do with the size of the black hole that might be in the center of it?
No, but what you're probably thinking of is called the sigma mass black hole relation, and that is the motion of stars in the bulge component. So only in the bulge, not elsewhere in the galaxy. If you look at the bulge of the Milky Way or the bulge of another disk galaxy, that correlates with the mass of the black hole. So the supermassive black hole seems to be larger when the bulge component of the galaxy is moving faster.
But there is no gravitational relationship between the outer stars and none at all?
No. Which is why
But
I was so curious at
what
first.
keeps them together? Yeah, I mean, in other words, if the outer stars are not being impacted that much by the gravitational impact of the density of the stars in the center of the galaxy and the black hole, what is actually contributing to keep them in a place that will keep them consistent within the structure of the galaxy?
So it's a combination of that, of the stuff that's interior, but it's actually dark matter. That's the reason why dark matter had to be invented, because there wasn't enough in the internal parts of the galaxy to keep the outer parts of the galaxy rotating as fast as we saw it rotating. That's the reason why.
So you're saying that dark matter has a gravitational
Absolutely.
effect on it?
Yes.
That's how
So
they-
that's why dark matter. So dark matter came about in the in the probably the between 70s and 80s, and it was because if you look at how fast the stars are rotating in the outer galaxy, they seem to be rotating at roughly the same speed as the inner galaxy, which makes no sense, right? Because Pluto's orbiting much slower, and so the only way to do that was to add more mass to the galaxy that we didn't see called dark matter.
Just quickly, did it do that within a plane? Or is there a 3D depth to those stars, or did it just do it in one?
So there is a 3D depth to the stars, but the thing is so far away that Gaia actually has real trouble, at least right now, in discerning that distance. It will do a little bit better when in the end of its nominal 5-year mission, but we still have to wait till 2022 for that. Any other questions before I move on? Right, so the last tool of the Galactic Archaeologist is the chemistry. And so that's a lot of my work. A lot of my work has been done on the chemical composition of stars. Some of you actually may recognize this. It's a Pink Floyd.
Dark Side of the Moon.
Yeah. And so we, of course, stars have different chemistries. We can see that. We can chemically fingerprint the stars, if you will. So how do we do that? You basically take the starlight and you break it into the rainbow by a prism or a grism or a whatever, and so you get this. So this is actually another image of. Does anybody know what this is an image of?
Sun.
Sun. This is another way of looking at the sun. So this is what would happen if you took the sunlight and you passed it through a grism or a prism. This is an example of that. You get various different absorption features, and each one of these absorption features is caused by a different element in the atmosphere of the star. And what you can do is you can measure the size and the shape of those absorption features and figure out how much, say, iron or magnesium or whatever is in the atmosphere of the star. And to someone who's trained, you can actually look at patterns like this, and you can actually say, this is magnesium, this is sodium, this is oxygen, this is iron, this is hydrogen in the atmosphere of the star. This, for example, is the beautiful H alpha. Right there. So I can look at this image and start to tell you, based on the colors, roughly what the elements are going to be. So I know this is H alpha. So this is hydrogen H alpha, which is a filter that's often used for solar observations. This, for these two doublets here, for example, are sodium in the atmosphere of the sun. So I can measure the size of this and measure how much sodium is in the atmosphere of the sun. And so that's what I spend most of my time doing. It doesn't look anywhere near as beautiful as this. I will just tell you that now. This is like the most beautiful thing I've seen all day, almost.
What created that?
Huh?
What created that image?
What created this? This is I think this was done by, I don't know if
Big
NASA
Bear,
does
doesn't it?
this, but I don't know if they do. Say again?
Isn't that Big Bear? I thought I saw that come out of Big Bear, that solar.
It might be.
I thought I saw it come out of there.
Yeah,
I've
I
seen
know.
one that just looks just like that. But
I don't know exactly how this is done. I mean, like, for example, these set of lines down here make me think this was done, wherever this was done was on the Earth. Because this is actually telluric lines coming from the Earth's atmosphere. But, I don't know exactly where this was done. That's a good question.
Now that's all wavelength. Is there amplitude involved in that, or?
Yeah. There's certainly amplitude involved. For example, I don't know how they've chosen to scale this, but the sun comes out mostly at green light, roughly, compared to red light, so it's not super red. M dwarfs, which is where we're looking for most of our exoplanets, they're much more red light than blue light. Yeah, that's a very good question. This is just showing some examples of what spectra look like for various different types of stars. And so these are some stars that you probably have either heard of or know of in the sky or have observed yourself from a telescope. And so, one of the really cool things about spectra is that the cooler the star, the harder it gets and the more lines you have. Because molecules are so annoying. They're great for human life, they're terrible for an astronomer because we can't model molecules very well. So by the time you get to Antares, which is an M1 star, you get lots of molecular features kind of obliterating your spectrum. And a star like Vega is an A0, there's almost no lines there because it's so hot, it's ionized all the lines away. So
really?
It's really quite cool actually to do stellar spectroscopy. This is a temperature sequence, so this goes from the hottest to the coolest. So from these spectra, we can actually piece together the chemical composition of stars. And so we go back to our periodic table. This is our, the periodic table we all know and love. Of course, this isn't the periodic table to an astronomer. This is a periodic table to an astronomer. Yep. Right. So there's hydrogen, there's helium, and there's metals. Because hydrogen and helium dominate by far the mass content of the universe. But the metals are important. Things like magnesium and silicon and calcium. These things are actually really important to piece together where stars come from. You can look at the magnesium content of a star and immediately tell if that star is coming from our galaxy or another galaxy because of the amount of supernova explosions that had to create that magnesium. And so here's a schematic showing kind of where the various different elements in our universe come from. Hydrogen and helium were kind of Big Bang. Lithium, beryllium, and a little bit of carbon. Boron was basically created also by cosmic ray spallation after the Big Bang. So very, very close after the Big Bang. Then you have, all your other elements that you know and love have come from various different types of stars or supernova ejections. And so as the universe evolves, it evolves from just having hydrogen, helium, and lithium. So this is the Big Bang. The universe only starts with hydrogen, helium, and lithium, which is quite boring, right? We wouldn't be here if that's the case. Then you create your first generation of stars. We call those the population 3 stars. They're probably very big, although we don't really know because we've never observed one before. They are very big. They die very quickly because stars die, big stars die quickly. Small stars die very slowly. Then they explode in supernova, and all of that material that they generated in their core then is dispersed into the interstellar medium. And the stuff that comes first are things like magnesium, strontium, nitrogen, silicon, titanium. That stuff all comes first. Then you have gas that's now polluted by all this stuff because you have supernova explosions, and that gas then forms the next generation of stars. And those generation of stars are called population 2 stars. And then those stars form, they live, they burn hydrogen to helium, they do all of their thing, they explode, and they create even heavier elements. And then this process keeps happening over and over and over and over again. And by the time you reach present day, you have things like uranium, europium, thorium, barium, lanthanum, yttrium that are all produced by very low mass stars. They're starting to kind of die and give their nucleosynthetic guts back to the universe.
So a low mass star had to be around where our sun is to create the sun because we have uranium.
Yeah, so by low mass I mean like 8 times the mass of the sun, 8 to 10 times the mass of the sun.
Okay.
High mass I mean like 100 times the mass of the sun. Okay. So to get uranium and these kinds of elements, inevitably, again, we actually really don't know how this forms because our understanding of nuclear physics is pretty poor, especially at these temperatures and pressures. But the idea of getting like things like uranium and thorium and europium, the idea is you take fairly low mass stars, in the order of about 8 to 10 solar masses. They live their life, they die, and they become neutron stars. And when you get neutron star mergers, those create either black holes or they can create very, very heavy atomic nuclei like uranium, thorium, europium, and so forth. And so you need these types of neutron star mergers, or neutron star X being some other type of star merger, if you want to get these types of heavier elements like uranium, thorium, and so forth. But again, it's still very hand-wavy because at this particular time, the nuclear physics is not very good for these elements.
Wow.
So we have a lot to learn.
Where in this did molecules get generated?
Oh, molecules get generated quite early on. And that's because a molecule like H2, for example, you just need hydrogen, but you also need it to be very cold. So molecules generally form in colder environments where you don't have the energy, because the molecules are vibrating. If you put too much energy, the vibrations will destroy the molecule. So as long as it's cold and you have the element already present, H2, here after population 1 you get C2 and CO forming. And so those molecules can form as long as it's a cold environment.
That's amazing.
The periodic table that you had before showed that iron can come from two places, one being a supernova, but the other being large stars. What large stars give out iron?
So that's probably supernova as well, because it's two types of supernova. One is called type 2, and one is type 1a. Type 2 supernova produce iron. Type 2 supernova are very large stars that go supernova. They basically collapse in on themselves and rebound off the core and create a big explosion. They create iron. There's another way of creating iron, which is type 1a supernovae, which is a white dwarf in binary with something. The white dwarf eats material, and if it gets enough material, you get thermonuclear reactions on the surface that rebound back off the core, and then you get the type 1a. Type 1a's are much lower mass stars, though, so it's two different avenues.
So you don't actually burn to iron?
You can burn to iron. More massive stars will burn to iron. The sun, I don't think will. More massive stars burn to iron, but they can't do anything with the iron afterwards. Right?
Because now it becomes a negative energy to continue.
It has the highest binding energy per nucleon. So you can't, it's an exothermic reaction in the sense that you need to dump lots of energy in if you want to fuse iron. The thing is, the iron, if you don't have a massive enough star, the iron will just sit in the core and it won't do anything. It will just be locked up in the core. If you have a massive enough star, then the outer envelope comes back down onto that iron core, it rebounds and shocks off, and then creates an explosion. Right, so I kind of want to finish in 10-ish minutes. 10
Whatever you like.
Yep. Just making sure everyone's still with me.
Keep going.
Oh, yeah.
Is everyone?
No, we're even
Okay.
awake.
Just want to make sure everyone's with me. All right, so what do these chemical elements tell us? And so this goes back to this idea of chemical tagging, this idea that we can tell that something comes from the center of the galaxy or the solar neighborhood or another galaxy entirely. And so this is the holy grail, in some sense, of galactic archaeology. Can you distinguish just by the chemistry alone, whether a star is coming from one place or another? Because if you can do that, then you can take a chemical fingerprint of all the various stars in the galaxy and actually piece together where they came from. And that would be really cool. Not just for the press, because the press always asks us, where are the sun's neighbors, right? So, and with chemical tagging, we could probably do that. So the idea is a little bit like this. If you have two stars, stars are formed by these giant molecular clouds. If you have two giant molecular clouds on opposite ends of the galaxy, they have different chemistry. So one is metal rich, has 2 times the iron content of the sun, and one is metal poor and only has 1/10. And those gas clouds form stars, but as the stars are forming, the gas clouds actually disperse because once the stars turn on, the winds from the stars blows away that gas. And as the galaxy evolves, those stars are interacting with other things, either other stars or other giant molecular clouds, and they're dispersing. So they get mixed up. And so it's a really hard problem. How can you tell that these stars that are blue are all born together, these stars that were orange were all born together? Because they're all mixed up, so how do you do it? And the idea of chemical tagging is you take a spectrum of this star, and this star, and the chemistry of these two stars is the same because they were born together in the same cloud. But the chemistry of these group and this star is different because this was born in a completely different cloud. And so that's the idea of chemical tagging, and it seems to work fairly well. We can actually use this idea of chemical tagging to piece together where the various stars are coming from and try to run back time to understand how the galaxy may have formed. And so this is really, I think, kind of the holy grail of galactic archaeology, and this is something that we're all kind of racing to do. Yeah?
When you find stars in a galaxy that you've determined are from another galaxy or from somewhere else, is it common or uncommon to find just a few or a lot?
It's fairly, there's a lot of caveats to what I'm about to say, but it's fairly uncommon in the sense that if you take a galaxy like the Large Magellanic Cloud, it's fairly uncommon to see stars from the Large Magellanic Cloud here in our galaxy. It's almost impossible to see them from Andromeda. And the reason is because, for example, for Andromeda is so far away, and stars only live for so long. So to be able to see a star that has been stripped off of Andromeda heading towards us, it needs to be very bright for us to be able to pick it out. Bright stars, though, are very hot and very massive. And massive stars don't live for very long.
Sure.
So there's not a good likelihood that you're going to see a star from another galaxy. That being said, if you look up in the stellar halo, there are galaxies like Sagittarius and other smaller dwarf galaxies that are actually currently being eaten by the Milky Way. And so there's tidal streams of material stripping off these galaxies coming into the Milky Way. And those we can see because they're much closer and they're much smaller systems.
Okay.
So there's a little bit of a caveat about that answer. Any other questions? Yeah.
I think it was 2 years ago at NEAF, I can't remember with the professor, but he showed a series of charts about F, E, and H, and saying this is not an easy measurement, the ratio.
The ratio of iron to hydrogen.
Right.
Earlier today I was deriving the FE over H, the iron content of another star somewhere else in the galaxy. FE over H is a challenge to measure. It's much easier than every other element, though, because if you ever look at a stellar spectrum, most stellar spectra, like the sun, the spectrum itself is obliterated by iron lines. There's tons of iron lines everywhere in a solar spectrum, and so it makes it fairly easy relative to something like europium. Europium or thorium or uranium's hard. Uranium's really hard. So comparatively, iron is easy, but it is still quite hard. But europium is or uranium is almost impossible.
And
but
you'd be looking at those chemicals because you'd be looking for first generation?
yes. So people who look for uranium lines or thorium lines often are looking for stars that have just maybe been polluted by 1 or 2 generations of stars. So there's that. But they're also looking to age-date a star using radioactivity.
Okay.
Same way of carbon radioactive dating, but you do it with thorium and uranium. It's just really hard to do because it's in the ultraviolet part of the spectrum, and so you need to go to the Hubble Space Telescope to get a spectrum.
And only the Hubble Space.
And pretty much only the Hubble at this point.
50% I think of pictures are now in UV on Hubble.
Yeah, and it's because you can't really see it from ground. It's hard to get from
And they're
ground.
not launching another one soon, a UV satellite soon.
I wish. JWST's taking all of our money.
Okay.
Yeah, so it is hard, but comparatively easy compared to other elements. Any other questions? All right. So I kind of want to spend the last maybe 5 minutes that I have talking about where I think galactic archaeology is going. And so the I think the next step of galactic archaeology is what I like to call chemical cartography. So does anyone know what cartography is? So chemical cartography is making a chemical map of the galaxy. So this is an example of what I mean. So in the background you have a simulation of the galaxy, not a real observation. And in the foreground is real data that we have from various different spectroscopic, or from one spectroscopic survey called the Gaia survey. And the color coding here is based on iron to hydrogen. The redder, the more iron there is relative to hydrogen, and the bluer, the less. And so what you're seeing is that as you go towards the galactic center, as we talked about earlier, you get more iron appearing. And as you look anti-center, going away from the galactic center, you have a lot less iron appearing. And if you go out, it goes from, you have, it actually gets a little bit less as well. And so this is not the best way of visualizing it, but one of the things that we're working with, one of the things I'm doing in collaboration with the American Museum of Natural History, we're taking the Gaia data, which has positions, 4 billion stars. We're putting that into the planetarium dome, where you can now, the hope is that so we just started the project, I hope in about a year or less.
Are you working with Carter?
Say again?
Are you working with Carter?
No, I'm working with Brian Abbott and Jacqueline Ferry, right? And so what we're doing is the first thing they're going to do is we're going to actually get that 3D map of the galaxy that Gaia is producing, so you can fly through it in the planetarium dome. But instead of painting the stars by their temperature, which is how they're painted now, so hot stars are blue and cold stars are red, is how they're currently painted. We're going to instead paint them by their chemical fingerprint. And so you'll be able, my hope in the next 6 to 12 months, be able to fly through a 3D rendering of our galaxy, painting every star by its chemical fingerprint, looking for really interesting structures. So I think that will be the next generation of galactic archaeology is doing this type of chemical cartography work. And I'm currently writing 2 papers for journals on chemical cartography. Right, so some takeaway points. I think galactic archaeology, I hope that you all kind of got out of this, that it's kind of the study of the formation and evolution of our galaxy using stellar fossils. I do think that galactic archaeology, while right now it's constrained to our own galaxy, I suspect that in the next 20 to 30 years, we'll actually be moving to galactic archaeology in other galaxies like Andromeda. We just don't have the telescope power yet to do that. I think, I hope that you have gotten a little bit of an idea of the tools, if you will, of the galactic archaeologist. That is the position, how we measure positions and motions in space, and how we chemically fingerprint stars, and how that information can be used to better understand the galaxy. I've talked a little bit about chemical tagging, chemical cartography is the future. But I kind of want to just say, because all of you probably already know this, galactic archaeology and astronomy is really just fun. And so one of the things that I've really enjoyed through my career as an astronomer is actually going to various telescopes around the world. So this one is in Palomar observatories in California. This one is in Arizona. These are the Keck and Subaru telescopes on Mauna Kea in Hawaii. And this is inside of Palomar, and this is one of the galaxies we were looking at. One of the things that I really loved about being an observational astronomer is getting the ability to travel around the world, do what I love, and trying to understand the galaxy and galaxies in general. And so it's good to see that you guys have a love for astronomy the same way I do. So with that, I'll kind of end and just say this is what Gaia actually saw. So this is the Gaia sky as of April 25th, and we look forward to really trying to piece together how this thing formed.
Amateur astronomy group, can we contribute to science with our telescopes? Can we do spectroscopy from here, or do we need instrument or telescopes much bigger like Palomar and the other telescopes that you're using?
One way that small observatories and or astronomical societies have been getting involved, for example, with Gaia, is one of the things about Gaia that I didn't talk at all about is that Gaia, because it goes back and stares at every star at least roughly about 70 times or more, because it has to look at the positions. And so one of the things they're finding variable sources, things that are exploding or brightening. And they're one of the things they need is for either small observatories or amateur groups to kind of re-observe these objects at higher cadence to see, is this interesting, is this not interesting? So this might be
star observing.
Yeah, variable star observing.
Okay, so we're doing that.
So variable star observing might be one thing. Asteroid follow-up would be another thing, although the asteroid aspect hasn't been something that was done in Earth.
And what is the asteroid aspect?
So they've been finding and characterizing the orbits of near-Earth asteroids.
Right.
I don't know, so this is very new because the first data release was in 2016 and they did not have this in.
Okay.
The newest data release was in April, and there was some claim that there should be some program to get citizen science involved in helping characterize the orbits of the asteroids.
Oh, okay, we do occultations.
Yeah, so I think that will be something that will be coming up. I'm not sure how far along that program is, but I do know they have a transient program going. Yeah.
So there was talk about looking for sun's twin.
Yeah.
What's the status of that idea?
So solar twins are hard to find. So one of the things that has been done with Gaia is that they're trying to find all of the stars that have either passed or will pass very close to the sun. Either from using the orbits, that the refined orbits from Gaia. I don't know how much progress has been made in the last 2 weeks on that,
Okay.
but I suspect to see a paper or two. I know that Jackie Faraday at the American Museum of Natural History has published a paper in the last couple of weeks talking about one of the nearest stars to the sun that could have been associated with the sun, based on this new data from Gaia. But I think it's still yet to be seen whether we'll be able to find the sun's neighbors, the sun's twins, if you will.
I mean, they could be spread across the galaxy by now, or...
Yeah, because the sun has been around for 4.5 billion years,
Yeah.
so it's done several orbits. It's done several orbits around the galaxy, interacting with stuff.
And when it goes around the orbit, it's not a flat line, it's like this.
Yeah, exactly.
Isn't that like they were talking about the fact that
Carousel.
M67 is a cluster that has got a lot of stars that are very similar to the sun? Have you ever heard of that? Or no?
I haven't. There's M67 it is very close in chemistry
Yeah.
to what the sun is. I don't know whether the two ways that people will do this is they'll either use the chemistry, so the chemistry has to match that of the sun, but then it's also the orbit analysis.
Right.
So you have to be able to track back the sun or M67 into the orbit so that they agree. I don't know whether or not that actually occurs.
Okay.
And
All right, good. Very much.